Hello again, everyone. This is Keith. I'm here to talk about Team 5's progress on designing a planar orthomode transducer, or a OMT for short, for our partner company ADCI, and of course with the help of our mentor, Dr. James Abele. You will also hear from Team 5's other members over the course of the presentation, being Hadley Butler and Miss Annabelle White. So stay tuned. We have lots in store for you. So in case you needed a refresher, our project came about because of ADCI's need for an improved design in the OMT that they currently use in their CMOS satellite receiver products, like the one pictured here. The current OMT is a significant contributor to input signal degradation, which is a real issue in high-definition signal reception. Our project therefore has two goals. One, to increase the quality of signal reception by exploring the use of suspended stripline components, and two, to decrease the overall size of the OMT in order to increase the number of signals a single CMOSat is capable of receiving. These improvements, we hope, will make ADCI more competitive in the marketplace. In this presentation, we will go over the following topics: a brief update on our budget, the prototype design work we've done so far this semester, and the future testing we have planned. We will also briefly discuss some additional concepts we are exploring that could potentially be beneficial to ADCI before wrapping things up. Now, starting things off on a very positive note, we are happy to say that we have kept to our original budget estimates and even managed to find some cost savings for our prototypes, since that firm of Rogers Corporation was willing to provide the team with the dielectric material needed to fabricate our circuit board prototypes. As previously mentioned, ADCI is covering any associated costs related to fabricating and testing of the prototypes, and we have been able to successfully perform all the necessary simulation testing with the Advanced Design System simulation software, which is a software freely available for all ASU students. Folks, at this time, I would like to hand over the presentation to Annabelle to speak about the prototype designs. I thank you so much for listening.
Thank you, Keith. At the beginning of this semester, we worked on finalizing our prototype designs with simulation software. On this slide, you can see one of the circuit board prototypes that will be manufactured and tested. This screenshot was generated in ADS, but you can imagine the black background as being the dielectric, which is typically the green part of a printed circuit board, and the red areas are the copper transmission lines. This circuit board contains three different key test pieces: a circular rat race on the left, a straight transmission line in the middle, and an oval or capsule-shaped rat race on the right. Two such boards will be fabricated like this, one with conventional strip-line, dielectric, and one with suspended strip-line, so that their transmission characteristics can be tested and compared. After we were happy with our simulation results, we created Gerber files, which are a type of artwork file that the printed circuit board manufacturer can use to bring our designs to life. After creating these drawing files and fabrication documents, we sent them to our mentor and ATCI for review and approval. We are currently wrapping up an iterative process in which we have received feedback from ATCI, changed some of our design components for the boards, updated the corresponding files, and then resubmitted them for approval. Some of the biggest changes were adding extra ground layers to the top and bottoms of both boards to accommodate the metalwork that will be used to secure the prototypes and allow for them to be tested. We also changed the designs from having solder mask to including something called HASL, HASL, or hot air solder layer, which just makes it easier to solder components to these circuit boards. In addition to the Gerber files, we also wrote fabrication detail documents and created fabrication drawings such as the one pictured on this slide. The current picture actually shows our conventional strip-line design, and it basically specifies how the dielectric and metallic layers should be stacked, as well as giving the appropriate thicknesses for the most recent and final change requested by ATCI was for both the suspended and conventional strip-line boards to have their terminations meet in the exact same locations. The conventional strip-line circuit layout is on the left, and the suspended strip-line is on the right. As you can see, on the circular rat races, the conventional board has one transmission line at top and two on bottom, while in the suspended strip-line circuit, there is one on top, one on bottom, and one on the left-hand side of the board. If you look at the oval-shaped rat races, you'll also notice that their port spacing up top is slightly different widths. Rerouting where these lines terminate to match on both boards will allow the placement of the connectors used to introduce signals to the boards to match. This change will in turn allow for the creation of only one metal enclosure for each of the boards, rather than two different enclosures, which will be more cost effective for ATCI and save them some fabrication time. We are therefore reshaping the conventional strip-line edge ports to match that of the suspended strip-line design, which we will be able to leave as is. We have sent these drawing files, along with the fabrication specifications, to ATCI for final approval, and we fully expect fabrication of the prototypes to begin shortly. These prototypes will be manufactured by Microcircuits Inc., a company of ATCI's choosing. I would like to hand things over to Hardley now, who will discuss the prototype testing we're planning, as well as some extra things we are working on, before wrapping things up.
Thank you, Annabelle. After Microcircuit Inc. fabricates our two prototype boards, they'll undergo various testing at ASU with the aid of our mentor. We plan to use a two-port vector network analyzer similar to the one pictured in this presentation that is capable of measuring S parameters for the test pieces that Annabelle mentioned earlier. To ensure the appropriate tests are performed, our team is developing a test plan that could be used as a guide when the laboratory tests are performed. Additionally, we are doing research into how to connect the signal ports to the network analyzer in a lab setting. To introduce input signals to our test pieces, we need connectors to attach to the signal ports and to the rest of the test bench setup. The picture here shows the different types of connectors attached to a circuit board. We will be doing something similar for our prototypes, although we'll be using only one type of connector. To select the appropriate connectors, our main considerations are given to how the signal will be introduced and how the connector will attach to the board. For our purposes, the signal will be introduced via a coax cable, and we will be soldering the connectors onto the board. A connector of appropriate height must be selected to accommodate the thickness of our different boards. In the case of the strip-line board, it is a relatively standard thickness. However, extra accommodations may be needed to put in place for the suspended strip-line board, which is much thinner. While we have some downtime waiting on the test pieces to be fabricated and delivered, we are doing some additional simulations that could potentially improve the transmission characteristics of the OMT even more in the future. This work has the potential to spark another senior design project partnership with ATCI. The thought is that while the suspended stripline design will most likely show improved transmission characteristics over the conventional stripline design, the suspended stripline design may be further improved by adding a second conductor layer on the bottom side of the dielectric and connecting the signal line to this bottom conductor layer. This could help contain the input signal to the metallic layers and prevent signals from bleeding out into the surrounding dielectric. In regards to the project schedule, there are a few deliverables that we are not able to complete within the predicted time frame and still remain open. These deliverables are found within the testing phase section of our schedule. This delay is attributed to the design phase of the project lasting longer than we have anticipated. There were multiple change requests from ATCI that were made, such as the change of the designated fabrication facility, to changes of the edges of the board to accommodate the use of one metallic enclosure rather than two separate enclosures, and etc. Although there are multiple changes and the project schedule is a bit behind, we are confident that we can still produce and test the prototypes before the project end date. To wrap things up, we would like to re-emphasize the impact our project will have. The improved design possibilities ATCI will acquire from our work will facilitate their competitiveness in an ever-evolving marketplace. Currently, our prototype designs are under final review and will soon be fabricated. Then, we can begin testing the prototypes and analyzing the results to see how much of an improvement in transmission characteristics the suspended strip line provides over the conventional strip line design currently used by ATCI. We are at the end of Team 5's progress presentation. If you have any questions, please do not hesitate to contact us via email. Thank you for your attention.